Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of July 2024. This question is from the section Complex Analysis, and the question is related to the application of identity theorem or uniqueness theorem. This question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704082. This question is also suitable for the aspirants of JL, DL, TS set, AP set, IIT JAM and GATE. Right. The given question is, let f be an entire function such that for every integer k greater than or equal to 1, there is an infinite set x suffix k such that f of z is equal to 1 by k for all z belongs to xk. We are given f is an entire function such that for every positive integer k, there is an infinite set xk such that f of z is equal to 1 by k for all z belongs to xk. Then which of the following statements are necessarily true? We are given four options. Option 1, there exists an infinite set capital X such that f of z is equal to 0 for all z belongs to x. Option 2, there exists a non-empty closed set x such that f of z is equal to 0 for all z belongs to x. Option 3, the set xk is unbounded for each k greater than or equal to 1. Option 4, if there exists a bounded sequence zk, k greater than or equal to 1, such that zk belongs to xk for each k greater than or equal to 1, then f has a 0. If there is option 4, if there exists a bounded sequence zk, k greater than or equal to 1, such that zk belongs to xk for each k greater than or equal to 1, then f has a 0. Right. Let's now discuss the solution of the problem in detail. We have f, an entire function, that is f, a function from C to C is an entire function. We are given for every k belongs to n, the set of natural numbers, that means k greater than or equal to 1, there exists an infinite set xk such that f of z is equal to 1 by k for all z belongs to xk. Note down that f is not a constant function. It is a non-constant function. Agreed? So it means to say for k is equal to 1, there will be a x1 and such that f of z is equal to 1 for all z belongs to x1. When k is equal to 2, there is an infinite set x2 such that f of z is equal to 1 by 2 for all z belongs to x2 and so on and so forth. And you note down that f is not a constant function. This fact we need in the course of the proof. Right. That's what we have concluded and call option 1. There exists an infinite set capital X such that f of z is equal to 0 for all z belongs to X. We also call option 2. There exists a non-empty closed set capital X such that f of z is equal to 0 for all z belongs to X. When we see this f of z is equal to 0 for all z belongs to X, if you are looking for a counter example, if you take f of z is equal to e power z, it will never 0 for any x. And if you want to get that f of z is equal to e power z as a counter example, you must verify the hypothesis. So e power z is an entire function, is all right. And for every k belongs to n, you have to show there exists an infinite set xk such that f of z is equal to 1 by k for all z belongs to xk. If you can do that, then that will serve you as a counter example, because f of z is equal to e power z is not at all not equal to 0 for any set x. Right? So let us let f of z is equal to e power z, an entire function. So now for k belongs to n, that means k greater than or equal to 1, let e power z is equal to 1 by k. This implies e power x plus iy is equal to 1 by k into e to the power of I 2n pi. This is 1. E to the power of I 2n pi in a complex notation. And for every n belongs to the set of integers. This is e power x into e power iy is equal to 1 by k into e to the power of in 2n pi. So that is e power x is equal to 1 by k and e to the power of iy is e to the power of I 2n pi. And therefore x will be minus ln k and y will be 2n pi. Y will be 2n pi. Then we choose capital x suffix k, xk is equal to x plus iy minus ln k plus I 2n pi, where n belongs to z. Obviously, as n belongs to z, xk is an infinite set. So, for every k belongs to n, there exists an infinite set xk, this one, minus ln k plus I 2n pi, n belongs to z, such that f of z is equal to 1 by k. F of z is equal to 1 by k. Thus, this function e power z is an entire function and has the property that is given in the hypothesis. Agreed. But e power z, f of z is equal to e power z, is never 0 for any z belongs to C. That means there does not exist a set X, let it be an infinite set, or let it be a non-empty closed set, such that f of z is equal to 0 for all z belongs to X. Thus, option 1 is not true, and so also option 2 is not true. Right. We now move to option 3 in the next slide. That's what we have. Option 3. The set xk is unbounded for each k greater than or equal to 1. Now, we provide a proof by contradiction. So, assume that this xk is bounded. Instead of unbounded, we suppose is bounded for some k. For some k, assume xk is bounded. Agreed. Let we define a new function g of z is equal to f of z minus 1 by k, z belongs to C. Now clearly, g of z is an entire function. Why? Because f of z is an entire function and minus 1 by k is a constant function, is an entire function. Therefore, the difference is an entire function. And g of z is equal to f of z minus 1 by k is equal to 0 for all z belongs to xk. So if you take a z belongs to xk, g of z will be f of z minus 1 by k. For z belongs to xk, f of z is minus 1 by k. 1 by k minus 1 by k is 0. So thus, xk is the set of zeros of g of z in C. And how this xk is? Xk is infinite. Xk is infinite. So now let's recall a theorem called identity theorem or uniqueness theorem. And suppose that f is an analytic function in a domain D, connected domain D. Keep that connectedness, that's a must. And if S, the set of zeros of f in D, has a limit point z star in D. So the zeros of f in D, suppose it has a limit point that is z star in D, then f of z is identically equal to 0 in D. So now the story has come here. G of z is an entire function, therefore g of z is an analytic function, right? In the whole of the complex plane. D is whole of the complex plane. And for S, we have xk, the set of zeros of gz in C. Yes. And now, what is xk? Xk is a bounded infinite subset of C. So xk is a bounded set and xk is infinite set. So thus xk has a limit point in C because xk is a bounded infinite subset of C, and we use Bolzano-Weierstrass theorem. So you are guaranteed xk has a limit point in C. So xk has a limit point in C. Therefore, by identity theorem, g of z is identically equal to 0 in C. Here D is C. That is, f of z, g of z is identically equal to 0 in C means f of z minus 1 by k is equal to 0 for all z belongs to C. Z belongs to C. This implies f of z is equal to 1 by k for all z belongs to C. That means f is a constant function, which is a contradiction. So this contradiction tells us that our assumption is false. Therefore, the option 3 is true. That is the proof by contradiction. Agreed. We move to the next slide for the last option. Option 4. If there exists a bounded sequence zk, k greater than or equal to 1, such that zk belongs to xk, for each k greater than or equal to 1, then f has a 0. We have a bounded sequence zk, k greater than or equal to 1, such that zk belongs to xk for all k belongs to n. Zk belongs to xk means f of zk is equal to 1 by k for all k belongs to n. Thus, we form a sequence f of zk. So, thus the sequence f of zk tends to 0 as k tends to infinity. Why? F of zk is equal to 1 by k tends to 0 as k tends to infinity. Thus, the sequence f of zk tends to 0 as k tends to infinity. Agreed. Now, since zk, k greater than or equal to 1 is a bounded sequence, every bounded sequence has a convergent subsequence. Yes, that's a fact. So, because it's a bounded sequence, it has a convergent subsequence, call it as Zn k, k is k greater than or equal to 1. So, let this subsequence converge to Z0 say. So, that means we have a subsequence Zn k which is converging to Z0. Now, what is f? F is an entire function. That means it is analytic. Analytic means it is differentiable. It is differentiable means it is continuous. So, now f of Zn k tends to converges to f of Z0 as k tends to infinity because f is continuous as f is an entire function And we use by sequential continuity, Zn(k) tends to Z0 implies f of Zn(k) tends to f of Z0 as k tends to infinity because f is continuous. Agreed. But what is f of Zn(k)? F of Zn(k) is a subsequence of the sequence f of Zk. But the sequence of f of Zk tends to 0. Then every subsequence of a convergent sequence is convergent and converges to the same limit. Therefore, the sequence f of Zk tends to 0. Therefore, its subsequence f of Zn(k) also tends to 0. Note that f of Zn(k) tends to 0 as k tends to infinity, since it is the subsequence of the sequence fzk converging to 0 as k tends to infinity. So that means to say f of Z0 is 0. Thus, f has a 0. Thus, the option 4 is true. Now, summarizing all the options, the answer to this question is options 3 and 4. That is the detailed discussion of the solution of a problem from the section complex analysis, related to the application of identity theorem or uniqueness theorem. My impression about this problem is that it is definitely a difficult problem. But it is a good one. I am sure that you have understood the solution of this problem. I thank all of you for watching my videos. Please like them and share them with your friends and colleagues, and subscribe my channel if you have not already subscribed. I wish you all the best. Thank you.